Welcome to the deep dive. Today we're journeying into some really deep cosmic questions.
We are. We're focusing on quasars.
Exactly, quasars. But specifically, we're tackling this, long-standing puzzle. Where does the long wavelength light come from in radio-quiet quasars?
Right, the ones without those huge radio jets. It's happening right at the heart, near the supermassive black hole.
And it's a question that maybe surprisingly has actually led to some, errors in how we model galaxies.
And solving it. That's been a huge challenge. I mean, the areas we're talking about are just incredibly small.
How small are we talking?
Less than 0.01 parsecs across. That's tiny. Like maybe 2,000 times the Earth-Sun distance.
Wow, okay, so way too small for our current telescopes to see directly.
Far beyond. Any millimeter wave telescope we have now just can't resolve that level of detail. We couldn't get a clear picture, basically.
Right, so if you can't see it directly, you have to get clever.
You do.
And that's our mission for this deep dive, unpacking a really ingenious solution, gravitational microlensing.
Yeah, using stars in a galaxy closer to us as a sort of natural magnifying glass.
A cosmic magnifying glass, allowing us to see these impossibly small structures. So we're going to look at some new observations that finally gave us a real geometric measurement.
That's the plan.
Okay, so microlensing sounds great in theory, but did it work? Let's dive into the specific case. RxJ 1131 1231.
Right, a distant quasar, and it's quadruply lensed, meaning we see 4 images of it. ALMA observed it back in 2015 and then again in 2020.
And what they found was pretty dramatic, wasn't it? A big change in its millimeter wave light.
Huge change, specifically the brightness ratios between the different lensed images. So how bright one image was compared to another.
Like the AD ratio.
Exactly. That AB flux ratio dropped significantly. It went from about 4.4 down to 2.7.
That's a massive shift. What does that tell you?
Well, what's really fascinating is that variability, that extreme change. It could only really be explained by microlensing. And microlensing of something incredibly compact.
Okay, so the changing magnification implied something tiny was being magnified.
Precisely. The data showed a half-light radius, basically, where half the light comes from of less than 50 astronomical units.
50 AU, that's less than 2.4 by 10 to 4 parsecs.
Yep, or think of it like this. It's about 46 times the black hole's gravitational radius. The event horizon's effective size.
So incredibly close to the black hole itself. And they ruled out other ideas, like the quasar just flaring up.
They did. They looked carefully at intrinsic flares or movements of the lensing galaxy. None of those fit the data. It really solidified the microlensing conclusion.
Okay, so it's almost unbelievably small, and microlensing let us measure it. But what is it? What's actually making that millimeter wave light in such a tiny spot?
The big question. And the evidence points pretty strongly towards one thing. The quasar corona.
The corona, like the sun's corona?
Sort of analogous, yeah. It's this really hot X-ray bright plasma, likely confined by magnetic fields, sitting just outside the accretion disk very close to the black hole.
And the size fits.
The size fits beautifully. And what's really compelling is comparing the millimeter wave brightness we measured with its X-ray brightness.
Okay.
They match up remarkably well with something called the Güdel-Benz relationship.
Yes, Benz. What's that?
It's a known correlation, basically, between how bright something is in X-rays and how bright it is in radio or millimeter waves. We see it for stars, for their corona.
And now for quasars, too.
Exactly. Yeah. It's really the first unambiguous evidence that these corona are the main source, the dominant source, of this long wavelength emission in these radio-quiet quasars.
Wow. So not just an estimate based on flickers or models, but an actual geometrical measurement, a direct sizing.
A direct sizing. It's a big leap.
That really is incredible, going from just models to actually measuring this thing. So help us put this size into perspective. How does it compare to other parts of the quasar we know about?
Good question. Well, this millimeter wave region, the corona, is much smaller than the accretion disk, the part emitting ultraviolet light. That disk is maybe 147 times the gravitational radius.
Okay, much bigger.
But the corona size, around 46 times the gravitational radius for the millimeter emission, is actually quite similar to the size of the X-ray emitting part of the corona, which is estimated to be around 26 times the gravitational radius. They're in the same ballpark.
So it lines up nicely with the X-ray picture.
It does. And this discovery, it has wider implications too. Think about it. This variable emission from the corona, which we can now measure, often wasn't really included properly in the standard models people use to study whole galaxies.
So not accounting for this extra variable light source could mess things up.
Significantly. It could lead to errors, maybe factors of 2 or even more when you're trying to estimate things like how fast stars are forming in a galaxy.
Just because you weren't accounting for this compact, variable radio source from this central black hole.
Exactly. We actually saw that potential error when comparing the 2 different ALMA measurements of RxJL131 itself. It shows this isn't just, a minor detail. It can really affect our bigger picture cosmic understanding.
So we've gone from just theories about these tiny, powerful engines to actually getting, direct measurements. It opens up a whole new view.
It really does. And it leaves us with a pretty important question, something for you to think about. Now that we can precisely measure these incredibly compact regions right next to supermassive black holes.
Using this cosmic magnifying glass.
Right. How might this change our fundamental picture of how galaxies actually grow and evolve over cosmic history? What other secrets are hiding in plain sight, just waiting for microlensing to reveal them?